Hi, guys. All righty. Okay, let's see how, good morning. Give everybody a second to join. I'm going to assume for the rest of the semester, the attendance is going to start to go down exponentially because that's what happens towards the end of the semester, but it is what it is. Oops. I'm going to apologize right off the top of the bat. I don't know what's wrong with my allergies, but it's like I think somebody woke or got up in the middle of the night and just injected mold into my nose. So, yeah, so much fun. So much fun. All right, so just real quick, let me show you guys the stats for the exam. So pretty good. I've never had this many A's before, so there's that. I'm not trying to say anything, but hey, there are some benefits for taking classes online, right? Anyways, so that's the deal. You're halfway through the class. This next chapter is, some people find it easier than the last exam material, or this next exam material, I should say. But the good news is exam 4 is not that bad. Okay, it's not that bad. Okie dokie. So we're going to start with chapter 20 today. Okay, and basically these are all acyl substitutions of carboxylic acid derivatives. Okay, with the exception of course, with the exception of nitriles, because we just talked about nitriles before the exam. Okay, but as always, you know me and my spectroscopy, I love this stuff, right? We're going to talk about spectroscopy just a little bit, and we're going to talk about something that we don't typically look at a whole lot of when we're doing spectroscopy. Okay, we're going to talk about infrared spectroscopy. Now, as an organic chemist, right, our bread and butter is NMR, proton NMR, to a lesser extent, carbon NMR. But, when I made something in the lab when I was in grad school, the very first thing I would do is I would run downstairs and throw that puppy on the NMR. Then once I confirmed that I made what I wanted to make, okay, then I would just collect IR data and other types of spectroscopic data, just as, as kind of like, documentation. Okay, but we don't typically use IR alone. But when we look at the IR, okay, the wave numbers, okay, of carbonyl compounds. Typically, you'll see these show up in a range between 1650 and 1850 wave numbers, okay, which is a huge range, right? That's a pretty decent range. And the reason there's such a huge range is because all of these different functional groups have different stretches. There are some overlaps, right? But in general, what you can see, if you've got something at 18 something, you probably have an acid chloride. And if you have something around 16 something, you probably have an amide. Okay. And so in terms of, we can take all carbonyl peaks and say they're going to come into this range. Okay. And then we can say, okay, well, if you're this functional group, you're going to be here, that functional group there, there, and there. And so it's just another piece of information. Okay. You should be familiar with all of these. Okay. The only one that we really haven't talked a whole lot about is the so-called anhydride. Okay, which is that species right there. Pardon me. Which is this species right here. And what we're going to see is we're going to have two different stretches. Okay. And the reason we have two different stretches is because we have two carbonyls. Now, I know, and I know that you know, that those two carbonyls due to symmetry are identical, right? Pardon me. However, with anhydrides, we see something happen in terms of the symmetry of the stretches. Now, symmetry of stretches is something I'm not getting into. If you're a chemistry major, you'll learn about that. Trust me, more than you will care to learn about. Okay. But, just 2 carbonyls, 2 stretches is all you need to know as an organic 2 student. That's all you need to know. Acid chlorides are a little higher. Okay. They're probably have the highest wave number out of all the carbonyl functional groups. And we're going to talk about that, but it has to do with resonance and resonance contributors. Okay. Amides are some of the smaller because of, guess what? Resonance and resonance contributors, right? And then we see that the esters and the aldehydes and the ketones are kind of in the same range. Okay. And again, guess what that has to do with? Well, resonance contributors and some inductive effects for the ketone. And then the carboxylic acid does something really crazy that I'm going to talk about later on. Okay. So I stole these from the internet because they're amazing. But if you notice, they've got some weird things in here, like so-called out of plane stuff and in the plane stuff. So when we look at stretches for IRs, the number of wave numbers for an individual compound is 3n minus 3. So n is the number of atoms. Now, that's a really big number, especially when you're talking about complex molecules. And so this is the whole part of IR where we have so-called, symmetrical stretches, and then we have asymmetrical stretches, and then we have in plane bending, and then we have out of plane bending and wagging and scissoring and all sorts of weird shit that we're not going to talk about. We're only going to talk about the main stretches. Okay. OH, we talked about this before. Okay. And we know that the OH for carboxylic acid looks very different than the OH for an alcohol. Like, we know that. Okay. So you need to know that. Okay. But what we've never talked about is this so-called dimer. Okay. And so if you remember, the carboxylic acid carbonyl is the smallest of all the carbonyl derivatives, with the exception of the amide. Okay. And the reason behind that is because of the so-called dimer. Carboxylic acids exist as this. It's called a dimer because of the hydrogen bonding interactions between 2 carboxylic acid groups. If it's in solution, obviously this is fluid. If it's in if it's a solid, okay, this is how these molecules will orient themselves when they're building the crystal lattice structure. Of course, good luck getting an IR of a carboxylic acid in the gas phase, but that's what we're looking at here. And so what that does is it weakens these carbonyl bonds. Okay, because these oxygens are accepting what? They're hydrogen bond acceptors. Okay, and so as a result of that, they are using electron density to form that carbonyl bond. I'm sorry, that hydrogen bond. Once they are using their electron density, they're to form the hydrogen bond. They're literally pulling it from the carbonyl bond. Okay, and we know that the wave number is equal to this equation here. Let's see, the speed of light. So this is mass. We don't care about mass, but this K here is basically bond strength. And so this dimerization, this weakens, okay, the carbonyl bond. As a result of that, what are we seeing here? Well, we're seeing a carbonyl stretch just a little bit further down on the wave numbers. Okay. And so that's interesting. And like I said, don't worry about all this other stuff that says in plane, out of plane crap. The CO stretch, yeah, that's kind of cool. But typically that's down there in the fingerprint region. So it's sometimes it's hard to see that guy. Okay. Sometimes it's hard to see that guy. Next one. Acid chloride. So this is another one of those words you don't need to know about, which is known as an overtone. Okay. Acid chloride. Now this has one of the highest, okay, ranges. Okay, so the acid chloride has actually has the highest range of any of the carbonyl species. Okay. Why is that? Okay. Well, we know that acid chlorides, all carbonyl compounds, can resonate. Oops. And so when we look at these three resonance forms, okay, this of course is minor. Oops, I forgot my positive charge. Okay, this of course is minor. I can't spell minor this morning. I do have bad allergies, but I made sure I only took one allergy pill today. Like, I was like very aware. This is like minor. Like, this is like hardly any contributor. Okay. We look at this. This is also a very minor. What is wrong with this is also very minor. Okay. And when we see this, we can also see this with the carboxylic acid, right, that we just talked about. We know that carboxylic acids can also form this resonance form here. Now, here and here, okay, these are basically the same type of resonance form, right? Got a negative charge on my carbonyl oxygen, and I have a positive charge on my heteroatom. Okay, and these are both minor contributors, right? The major contributor is the double bond to the carbon oxygen, the carbonyl bond. Okay, and so why do we see such a difference between the carbonyl stretch here? Okay, this halogen, all halogens, okay, are very unstable as a halonium. Okay, halonium. You know what a bromonium bridge is? Well, that's what you call it when it's a bromine that's a positive charge. If it's C, it's chloronium. And so the generic name for it is just simply halonium, X plus. Okay. And it doesn't really make a whole lot of sense because we know that oxygen is more electronegative than chlorine. Okay. And we know that, because chlorine is less electronegative, okay, it really doesn't care for this type of a positive charge. It can't handle it as much. Okay. And so in particular, even though fluorine is more electronegative than oxygen, there's something else going on here that we can't really explain with what you guys know. Okay, you have to look at something else that I'm not prepared to talk to you guys about. And so again, the only thing that you need to know as an organic 2 student is this really right here doesn't happen. That X plus doesn't really happen. And so as a result of that, this carbonyl is mostly like this, the double bond. Okay, so it's like 99.999999999% as a CO bond. Okay, CO double bond. And as a result of that, this K value as an average, right? This K value for the bond strength as an average for an acid chloride is a little higher, right? Double bonds are stronger than single bonds. We know that. Okay. And so that's why acid chlorides look like this. Now, acetic anhydride, very simple. You don't have any hydrogen bonding. The resonance forms here are pretty straightforward. Nothing to see here, very simple. They are symmetrical, right? I can take a lone pair and go this way. Oopsie. Or I could resonate the other direction. And so what you'll see if you go to the interweb, what you'll see when you go to the interweb, what you're observing here is this and this simultaneously, right? Because both of those resonance forms are equal contributors. And when I say both, I mean this one and this one, right? Due to the symmetry of the molecule. However, that's a very simplistic way to explain something, and that's not what's happening. Again, if you are a chemistry major, we will explain this to you, but easiest thing to remember, okay, I have an acid chloride. I'm sorry, I have an acetic, and I have an anhydride rather. I have 2 carbonyls, which means I have 2 carbonyl stretches. Okay, simple, simple. Anytime you have a molecule with 2 carbonyls, you're going to have 2 carbonyls peaks. And so if you're in my chemistry lab, my organic 2 lab, we made a compound that had 2 different carbonyl peaks too. So one of the things you had to do was assign them, right? All right, if you remember that. Now, esters, not that special. Okay, they're right smack dab in the middle of the range of where we'd expect carbonyl stretches to belong. There's only one because there's only one carbonyl, and it's higher than a carboxylic acid, which is what it's always compared to. Esters and carboxylic acids are always compared to each other. Okay, and the reason it's higher is because it can't dimerize. Okay, this cannot dimerize. Very simple. The last one we're going to talk about, okay, is the amides. Okay, is the amide. And this is for a primary. And so something we see for a primary, so a primary amide is that I have these 2 nitrogens, I'm sorry, I have these 2 hydrogens. So I'm going to have 2 different nitrogen-hydrogen stretches. And as a result of that, okay, I have 2 carbonyl stretches, and they are referred to as the 1 or the 2 band. Now, here's the funny thing. If I have a secondary or a tertiary amide, then I only have 1 carbonyl band. Okay. And the reason it's so low is because it's even less electronegative than oxygen. So as far as amides go, they really hate this resonance form right here. When I say hate, it means it's a high energy resonance form. So it's a very, 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 very minor contributor. The 2 bands, again, if you want to know why that happens, we can talk about it in office hours, or you can switch majors and take physical chemistry too, which I'm guessing none of you do. Okay, and so here's some other stuff. I mean, again, 99.9% of you guys will never need to know, okay, what this means. But it does have something to do with, you know, confirmations, and you can read about this, blah, 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 blah. Okay, this is a great website. It's called chemlibrarytext.org. It's a really good website. I know you guys like to go to the Google a lot and look shit up, but there's really a lot of bad information out there. Okay, there's really a lot of bad information out here. So if you're going to go look something up on the internet, make sure it says .org or .gov. Okay, I know that some of these are more interesting to watch, but some of the information is highly watered down or wrong altogether. Okay, so that's it. We're going to introduce some new functional groups. So we're going to talk about those real quick. Okay, first one we're going to talk about is anhydrides. It's so funny because we just used an anhydride yesterday. I'm sorry, we didn't use it. We were prepping it yesterday for our next lab. And again, those of you guys that are in the organic 2 lab, you're going to be using these. Well, you're not going to be using these. you're going to watch somebody use these on the video, right? So these anhydrides, okay, they're excellent. Typically, we use them for acylation. Okay, what does that mean? I can take this group right here and add it to a functional group, for example. Oops. If I have this guy here, I can add that orange acyl group on here. So I've acylated this oxygen atom. That's where that word comes from, acylation. Okay, and then the byproduct of this, of course, is going to be, in this case, acetate, but any carboxylate will be its leaving group. So this will be the leaving group. So it's a substitution reaction. Okay, they come in a couple of different flavors. Okay, this one is called symmetrical. Okay, and of course, the flip side would be what? Non-symmetrical. I mean, big shock there. And so this would be an example of a non-symmetrical. Okay, something along those lines. Okay, they also come as cyclic. Okay, and we've actually seen one of these anhydrides maleic anhydride. Where did we see this? We saw this guy a lot in one of the chapters. I feel like I'm doing all the talking, because I am doing all the talking. Do you guys remember where we saw maleic anhydride? If you're in the lab, it was the starting material for one of your reactions. Does anybody remember? Does it ring anybody's bells? 61 A's on this last exam. I expect one person to at least be able to answer this question. And it's from chapter 19. No, it's not. It's a dienophile. It's actually one of the best dienophiles we have. Okay, and so it's an excellent dienophile, which is why we used it in the organic 2 lab. Okay, and so this is a very common anhydride that you're going to see a lot. Okay, let's talk a little bit about esters. Now, we've talked a lot about esters, right? But we also have cyclic esters. And they come, pardon me, they come in a couple of different flavors as well. Okay, they can be part of a 6-membered ring. Okay, they can be part of a 5-membered ring. And they can be part, oops, okay, so this is where I don't know what it is about me and triangles. Maybe if I do it this way. Oh, there we go. 3-membered rings. Okay, and of course, the different ring sizes can vary, but when they're cyclic ethers, when you're cyclic ethers, they're called lactones. And what we do is we count from the carbonyl, okay, away from the oxygen atom. So we don't count the oxygen atom, and we call them alpha, beta, gamma, delta. And so since the oxygen atom is attached to the delta carbon, this is called a delta lactone. And of course, this one would be what? What would be the 5-membered ring one? How would we call that? Yeah, exactly. It's gamma. Okay. And basically all this tells you is the size of the ring making up the lactone. And so of course this one would be what? This one would be a beta lactone. Okay. And so we also have cyclic amides. Okay, and they come in the same flavors as their cyclic ethers. Okay, only they are called lactams. And we use the exact same. Is that floating E? Yeah, I don't think that E is supposed to be there. Those of you that watch me and read my stuff, do you notice like randomly leave E's out and randomly put E's in? Has anybody ever read my stuff? I don't know what it is about me and E's. It's like, and I know I do it. I don't know why. As mom always says, there's only so much room on the hard drive. Maybe she's right. Anyways, we use the same type of naming notation for lactams that we do for lactones. So look, there's an E in the lactone too. It's not supposed to be there. So how would I call this lactam that I just wrote? How would I call this lactam that I just wrote right here? Yeah, exactly. It's a delta lactam. And so we would use the exact same notation, naming notation for lactams that we do for lactones. Okay, so nothing horribly difficult here. It's pretty straightforward. Now, lactones and lactams are very prevalent. Okay, they are very prevalent in biochemistry. And so you need to be familiar with this notation, because I'm going to tell you guys right now, when you go into biochemistry next semester, for those of you that are taking it next semester, all right, they're going to expect that you know all this stuff. And you should know it, right? Because you're going to pass this class. Okay, so make sure that you're familiar with this type of nomenclature, lactones, lactams, and we're going to go talk about some more biochemistry later on in the semester. All right, so this whole chapter is nothing but acyl substitutions. And with an exception of a few, they are all very, very easy. Okay. And so with say acyl substitutions, with any substitution, what do you need? You must have a good leaving group. Okay. The molecule can either come with a good leaving group, or what we can do is do what? Okay, we can turn a bad leaving group into a good leaving group, which we've been doing since chapter 9, right? When we were taking our alcohols and turning OH, which is an awful leaving group, and turning it into a better leaving group. That's what we're going to do here with these so-called bad leaving groups. In terms of their relative reactivity, okay, in terms of their relative reactivity, in terms of acyl substitution, acid chlorides are the most reactive, followed by these so-called anhydrides, okay, followed by alcohols, which are about the same as esters. So everything here is new. I'm sorry, everything here is not new. Okay, it's the exact same order that we saw, and of course these could be R's as well, so it could be primary, secondary, or tertiary. Okay, now we talk about leaving group ability. Okay, what makes something a good leaving group? Like if you had to sum up a good leaving group in one phrase that would encapsulate all leaving groups, what about its basicity? You're right, but what about it? It needs to be what type of a base? Weak or strong? Very good. Very good. So all good leaving groups are weak bases. Okay. And so when we look at weak bases, we don't really look at pKb's much. I don't know why we don't, because it would make life a lot easier. We're going to have to look at the conjugate acids, pKa's. Oops. Okay, we're going to look at the conjugate acids, pKa's. And so I'm going to just go ahead and I'm going to exchange this Cl for an X. Because, like I told you, I want you guys to realize that we're using acid chlorides in the Smith textbook, but there are also acid bromides. And I don't want you guys to see them and freak out. The chemistry is exactly the same. Okay. And so X in this case is going to be equal to bromide or chloride. Okay. And so this would be our leaving group. And so the conjugate acid of bromide, of course, is HBr. The conjugate acid of chloride, of course, is HCl. We'll look at the pKa of bromide, it's -9. Okay, HCl is -7. I mean, and so these are strong acids. So their conjugate bases are going to make what? Excellent leaving groups. Okay, excellent leaving groups. And that's why we use these so-called acid halides. As a matter of fact, we do not use acid halides in the Organic 2 lab because they are such good leaving groups that they just fall apart too easily. And so you have to have special care to handle them. And we don't have that type of equipment in the Organic 2 labs. So we never use them. And not to mention the fact I don't want to get gassed. Okay. And so the leaving group here is this halide, and the leaving group for my anhydride would be this carboxylate. Okay. So in this case, hold on, let me. Okay. So here, my leaving group would be this. The conjugate acids are carboxylic acids. And what type of a pK range are we looking at here? What type of pKa range are we looking at here for carboxylic acids? It's a range. Yeah, about 4 to 5. That's what I was looking at. Yeah, exactly. You're looking at about 4 to 5. And so as far as leaving groups go, these acid chlorides and these anhydrides can undergo acyl substitution without a catalyst. So without a catalyst, right? Because why? Their leaving groups are conjugate bases of acids. Okay, their leaving groups are conjugate bases of acids. And they don't even need to be a strong acid, right? We know that carboxylic acids are not strong acids, but we know that the acetate anion or carboxylate anion is pretty stable. The rest of these need to be catalyzed. Okay. And so when I start and I look at these leaving groups for my carboxylic acid, my leaving group is what? Hydroxide, right? Horrible. Its conjugate acid, of course, is water. Its pKa is 15.7. Yucky, yucky. Okay. The leaving group for my ester would, of course, be an alkoxide. Okay. Its conjugate acid is alcohol. And so we're looking at pKa values between 15.5 and 18. Okay. The leaving group for my amides would be amides. Remember, these can also be R's. And so now their conjugate acid would be ammonia or amines. And now we're looking at pKa's between 3.38 and 40. Okay. So the second set, carboxylic acid derivatives, they must be catalyzed. Okay. They must be catalyzed. Because why? Because their leaving groups are horrible. Okay, their leaving groups are horrible. Okay, now what we are going to find though is a lot of these reactions, especially with the acid chlorides, acid halides, and the anhydrides, they're exactly the same. They are exactly the same. Okay, and so just real quick, a non-catalyzed acyl substitution reaction is I'm going to start with something like this. I'm going to react it with a nucleophile, nucleophilic attack, formation of this tetrahedral intermediate, kick off my leaving group, and voila. This is a substitution reaction. Very simple, very simple. Now, for acid chlorides, they undergo probably the largest variety of acyl substitution reactions. Okay. And again, you're going to find that this is an incredibly simple section. I can't draw a straight line. All right, so we can do reactions with a carboxylate. Okay, and we get an anhydride. So reaction number one. Reaction number two. Oops, there should be an arrow there. Okay, is with water, good old fashioned H2O. And this typically uses a base referred to as pyridine or TEA. Does anybody remember what TEA means from last semester?
Triethylamine?
Triethylamine. So TEA equals triethylamine. Let me write that down here. TEA equals triethylamine. And it's basically used in the same capacity as pyridine, as imidazole. Oops, I always forget to where to put the double bond. I can't draw imidazole right now. Is it here? I don't remember. I think it's here. There we go. Anyways, imidazole. I'll just write it down here. And so basically, anytime you have these amines as solvents, typically what we do with those is we just use them as a source to deprotonate something. Okay. And so that's what you see. When you see bases as solvents, these are just there to do a deprotonation. Okay. All right. And so another option would be an alcohol. Oops. ROH, which would give you, of course, an ester. And of course, we could also take 2 times an amine or ammonia, primary or secondary amine. We need a secondary or a primary because we have to do a deprotonation step here. And that would give you that. Okay. And that would give you that. Okay. So the reactions of these are very, very simple. Incredibly simple. Okay. And fortunately, they're very similar to each other. So let's look at the reaction of this acid chloride with sodium acetate. Okay. And there's a solvent here. So don't worry about the solvent. What's going to be the first step of this reaction? It's going to be the first step of this reaction. Nucleophilic attack. Very good. Yeah. So I know that my acetate can come in and do this. I'm going to break my double bond. I'm going to form this tetrahedral intermediate species. I'm going to have my new bond here. I'm going to have that. And what's the next step? And consequently, the driving force of this chemical reaction. What is the next step in the driving force of this reaction? There you go. Yep. Reformation of the chlorine, I'm sorry, the carbon oxygen bond, chloride leaves, and voila. I mean, this is about as easy as it gets this chapter. Boom, right? Of all of organic chemistry, which is simply this easy. Okay, so that's it. And we have to remember that acetate comes in as an anion, right? I've got a negative charge here. But all of these other nucleophiles that we use, okay, all of these other nucleophiles that we use, like so the water, the alcohol, and the amines, or in this case, the ammonia, come in as neutral species, okay? And so if we do this exact same reaction now, with 2 times diethylamine, okay? So remember, from when we're doing this, we're using amines, we need to use what? 2 equivalents, okay? What are we going to see? Oops, you know what I forgot to do? I forgot to add the pyridine to the alcohol. Sorry about that, folks. All right. And so we've got 2 equivalents of the amine. So what's going to be the first step here? What's going to happen here for this reaction right here? What's the first step? Yeah, I mean, exactly. These are non-catalyzed reactions, right? So I don't have to catalyze them. I've got great electrophiles, right? So I'm going to see nucleophilic attack. Oopsie. I'm going to form this intermediate species here. New bond. This guy here. And so what's going to happen next? What's going to happen next? What do you guys think? Right. Leaving group leaves, we're going to reform the pi bond. So sometimes you guys are going to feel like, well, maybe I should do a proton transfer, because last chapter we were flinging protons all over the damn place. Remember that? But we're not going to do any proton transfers. So we're going to, again, leaving group leaves as the pi bond reforms. And so now I have this guy here. Again, new bond. Here. Now, why do you think I need 2 equivalents of my amine? Why do you think I need 2 equivalents of my amine? What do you think is going to happen next? What do you think is going to happen next? And it's why I need two equivalents of my amine. Come on, guys. Yeah, I need to get rid of the H. And who does that? Cassandra, you're right. Who does that? Nope, not chloride. Who's the strongest base in your system? Is it chloride or the other equivalents of diethylamine? Right? You have two potential bases in your system. Right? You have two potential bases in your system. You have chloride and you have another equivalence of diethylamine. So these are your two bases. Well, which one is strongest? Well, look at its conjugate acid, HCl and triethylammonium. pKa of HCl is -7. What is the pKa of triethylammonium? What is the approximate pKa of triethylammonium? The approximate pKa. I started asking you guys to remember the pKa of ammonium. I just told you guys to start remembering this one. Nope. No. That's a common mistake, Alan. This has a pKa of 38. Notice how there's no charge here. Notice how there's no charge there. Yes, about 9.2. That's exactly right. So the 10 is about the pKa here. So that's a good guess. Okay. And so 9.2 is the one that I wanted you guys to remember because this is going to serve as your frame of reference. Pay attention to the charges. Charges matter. Okay. And so the other equivalents of the triethylamine will come in. And then after this very long, arduous conversation about who does what, we form our final product, which is a secondary amide. Sorry, it's a tertiary. My bad. I don't know what it is about amides. I always forget to count the carbonyl carbon. I always forget that too. See, we all make mistakes. All right, so anyways, so why can't, if I were to do this, right? Let's try methylamine. I would get no reaction. Why? Why would I get no reaction for this particular scenario? Any ideas? Okay, it is tertiary, but why is that significant? Why is it significant that it's tertiary? And nucleophilic, yeah, it's pretty crowded, but what's even more important? What's even more important? Okay, so let's go through the reaction. Sometimes it's better just to go through the reaction. So I'm going to get here. Okay, it's going to give me this. Okay. What's going to happen next? I reformed this, but then what is my final product? Now, what do you think? Now, what do you think? Now, why don't you think why don't we use tertiary amines? Did you guys use all your brain juice yesterday? You guys like, is your brain like recovering from lactic acid poisoning? No hydrogen. I can't deprotonate, right? I cannot deprotonate. Okay. And you're right. Probably sterics is going to play a big role too. It's difficult to say if you'd even get to that point. The argument could be made that you wouldn't. Who knows? Cannot deprotonate, right? So you must have either ammonia, a primary, or a secondary amine. You can't use this with tertiary amines. Okay. All righty. Now, here's the great news. We are now going to talk about the reactions of anhydrides. And guess what? Everything is exactly the same except for the leaving group. Looky there. Looky there. Everything that we just talked about, okay, with acid chlorides, only we don't typically react them with carboxylates. So we'll take off this top reaction, but everything else is the same. Everything else is exactly the same. No difference. The mechanisms are exactly the same. Did I forget the water upstairs too? Did I forget that? Oops, I did. See, sometimes I get so excited, I forget to write stuff. My bad. Okay. And so, actually, let me put this, sorry. Can I fit it there? I can. There we go. All right. One less page to print out, right? All right, so let's talk about this. So let's look at the reaction with water. Okay. And so we're going to use ethanol. We're going to use pyridine here. So again, it's no different. Let's do this. Actually, let's not do that, because your book doesn't do that. I don't want to show you. So let's do this. We're going to react this in the presence of water. And we're going to use pyridine. Which is this guy right here. First step. What is the first step in the chemical reaction? Nucleophilic attack. Does it matter which one of these carbonyls I attack, by the way? Actually, does she use pyridine? I don't think she does use pyridine. Let me double check. I don't think she does use pyridine. There's so many different ways you guys can do this stuff. It's what you should be focusing on is nucleophile and electrophile. Let me double check. Oh, come on. No, she does not use pyridine for this. There we go. All right, nucleophilic attack. Again, does it matter which one of these I attack? Of course it does not. Due to the symmetry of the molecule, I can attack either one of these carbonyls, and you don't have to worry about that. All right, so we've got our new bond. What's going to happen next? Right, exactly. Reform my carbonyl bond. I'm going to kick off my leaving group. Now, in this case, my leaving group is acetate, right? So this group right here is my acetate leaving group. It's going to come off as a negative species. Okay. This carboxylate, I'm now going to have this guy here. New bond. Water. Still attached. Still positive. And so since I don't have a base, okay, the acetate will be the species that deprotonates and forms my final product. Simple, right? Simple. And so I guess the key thing to remember here is you don't really need a base because acetate's a better base than chloride is. Okay, so for the acid chlorides, your leaving group is Cl minus, and it's not a good base at all. Acetate's not a bad base. Okay, because remember the byproduct of this is what? Acetic acid, pK is 4.8. The pKa of this intermediate species right here is about negative 1.7. So it's totally strong enough to remove that. Questions, comments, concerns? Questions, comments, concerns? No? How are you liking this stuff so far? How are you liking this stuff so far? It is. So don't think it's some sort of trick. It's not bad. It is not bad at all. All right. Now let's talk about reactions of carboxylic acid. So actual carboxylic acids. Okay. Okay. And so we're going to bring out some old friends and we're going to see some new stuff. Okay. We're going to bring out our old friend. Oops. Sockle. Sockle. You guys remember Sockle from last semester? Formerly known as thionyl chloride, which that is a Cl that doesn't look anything like a Cl. Okay, it's going to give us an acid chloride. Okay, we can take this guy here. Hold on. 1, 2, 3, 4, 5. Add a little heat and get a cyclic anhydride. We can take a carboxylic acid, react it with an alcohol, in the presence of an acid and get an ester. And this one I call total horse shit on, but your book talks about it, so I'm going to show it to you, but I say BS. Reactions with ammonia ×2. Okay, a lot of heat. And somehow you're going to get an amide, which again, I call bullshit on. But we can take ammonia react it in the presence of this compound called DCC. And I've actually done this reaction 100 times, and it's a beautiful reaction. And we can form an amide that way. Okay. Alrighty. So these are the reactions of the carboxylic acids. Okay. So these are all catalyzed, okay, or driven by heat. Okay. And so Sokol is probably is the only one that's not a catalyst. Okay. Ethynyl chloride doesn't need to be catalyzed because of the formation of the byproduct. Okay, but DCC is a catalyst. Okay. Proton is a catalyst. Now, then we use heat. Heat has the same effect as a catalyst, right? It doesn't lower the energy of activation, right? It just gives you enough energy to get over the barrier. This is how I explain the difference between a catalyst and adding heat. All right. So anybody watching the Tour de France besides me, as you guys know, in case you didn't know, I really like sports. And so yesterday they were going over this ginormous mountain. Okay. So these little guys are bicycling over the mountain. Okay. What a catalyst does is it takes the mountain and it cuts it in half. Okay. So now instead of like this is what you have. Okay. What heat does is you take your little bicycle and you put a rocket on the back. Okay. So now you've got this guy on a bicycle, which I'm not even, should I try to draw a bicycle? Do you want to see me try to drive a bicycle? So this is a bicycle. And this is a guy on the bicycle. And then we're going to put a rocket on his bicycle. Okay. So that's the difference. Okay. But they both do the same thing. They allow you to overcome an energy barrier, either by lowering it or giving the system an extra little oomph. Okay. So the first one we're going to talk about is the formation of the cyclic anhydride. So we're going to take a dicarboxylic acid, and we can form a 5 or a 6-membered oh my gosh. Cyclic anhydride. Okay. Pretty much everything we're going to be doing in terms of ring formation, we can do 5 and 6-membered rings all day long. Okay. Once we start to deviate from that magic number, okay, it gets a lot more difficult to do. Okay. But to be fair, you know, this isn't anything that we really haven't seen before. Okay. The first thing we're going to do is we're going to add heat. And the purpose of the heat is to allow free rotation. Now, this is how your book shows it. Your book shows it like this. Okay. Already in this conformation. I showed it to you the other way because why? I want you to realize that you may not always get it in the prettiest conformation on one of your exams. What's important though is that you count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then of course, this would be my new bond. Okay. And then this and this need to go bye-bye. Okay, it needs to go bye-bye. So we're going to have an intramolecular nucleophilic acyl attack. Proton transfers. Water's going to leave. Okay, and it doesn't matter how you do it. Okay, and this is very similar to some of the stuff we did last chapter. Okay, and this chapter. So it's not really anything you haven't seen already. First step is nucleophilic attack. And again, it doesn't matter which one of these oxygens you use or which one of these carbonyls you attack. Only you can't attack the same carbonyl that it's attached to, obviously. Okay, I'm going to get this intermediate species. No, I'm not. I'm going to get this intermediate species. Okay, so this is where we're at right now. What do you think needs to happen? What do you guys think needs to happen? Ideas? Come on, help me out here. Deprotonation. Okay, and what else? What else? How about a proton transfer? How about a proton transfer? Oops. How about a proton transfer? If we I don't know why I did that. If we reform the carbonyl, right, we're just going to go back the opposite direction. We need to do a proton transfer here and not like I originally did, and not here, because why? I need to form a good leaving group. That's exactly right. That's exactly right. And so what I'm going to do here is I'm going to move this hydrogen over there. I'm going to get this guy here. Right, only half of what. I hate it when that happens. I'm going to get this guy here. And for whatever reason, my negative charge didn't come with it, but here we go. I'll just throw it on there. And now, well, that should be a positive, obviously. And now we're going to reform our carbonyl and kick off water. And that's it. And so that's how we form our cyclic anhydride. Questions about this? I'm not going to lie. Some of these reactions we show you, they're not the greatest, right? If I were to do this in the lab, I'd probably just let it cook over the weekend, right? It's going to take a long time. I got to get conformational change. I mean, do you think that this might happen? Do you think I could reform my leaving group here? Right? And then go the opposite direction, go back to where I started from? Yeah, every single one of these steps is an equilibrium step. Okay, every single one of these steps is an equilibrium. Okay, until well, not even until, and that includes the formation of the final product. This is pretty stable. But again, once I get to that point, I can still go in the backwards, right? A water could come in, attack, and do all sorts of neat shit. Okay. So questions about that? Questions about that? Okay. The next one is probably one of the most famous reactions ever. And again, if you're in the lab, you just did it, and it's referred to as the Fischer esterification. Now, the Fischer esterification takes carboxylic acid, reacts it in the presence of an alcohol, it is acid catalyzed, and we form an ester. And there we go there. Okay, and there we go there. Why do we use acid as a catalyst? Why do we use acid as a catalyst? Any ideas? When we have a strong acid in our system, so this could either be H2SO4 or TSOH. Typically, what do we do with these acids? Come on, guys. Protonation, exactly. Okay, so we're going to protonate the carbonyl oxygen. And the reason we do that is to do what? Well, make it more electrophilic. So now we have this right here. Okay, this makes this carbon here more electrophilic. Because now this particular resonance form becomes a larger contributor. I'm not saying it's a major contributor. I'm just saying now it contributes more, right? So that resonance form that I just drew right there. And so now, okay, this form will contribute more. And that's important. Okay. These are not very good electrophiles, right? Carboxylic acids, esters, amines, or amides rather, none of those are good electrophiles. Okay. The carbonyl carbons are being shielded by electron density from their neighboring Z groups, right? When I say shielded, I mean by resonance. Okay. And so they're not very good electrophiles. And so when we protonate the carbonyl carbon, it allows this particular resonance form to contribute more. And when I say contributes more, remember, these individual resonance forms do not exist at all. Okay, but what I see here is I'm going to have less electron density surrounding the carbonyl carbon. I have less electron density surrounding the carbonyl carbon. That makes it more attractive for a nucleophile, because at the end of the day, what do we know about the nucleophilicity of alcohols? What do we know about the nucleophilicity of alcohols? Are they good nucleophiles? Are they okay? Do they suck? You know, are they non-nucleophilic? What do we know about alcohols in terms of their nucleophilicity? Are they good or bad? Good or bad? That's all I need to know. Good or bad? What do you guys think? Yeah, they're poor nucleophiles because they're neutral. Yeah. So we need to help these puppies out. Okay. And so once I do that, of course, the alcohol can attack. So let's go ahead and let's look at a real reaction. Okay. Let's look at a real reaction. I'm going to take benzoic acid. How many of you guys are actually in my lab? The Organic 2 lab. Do I have anyone that's in the lab? Okay. So yeah, we did this, right? It was unknown, which made, you know, so we're going to do this with the presence of ethanol and acid catalyzed. First step. Anytime you have a strong acid, your first step is always going to be protonation. And you're going to always protonate the carbonyl carbon because why? Because of resonance stabilized. We talked about that last time. Okay. Now, obviously, so I have these two resonance forms here and here. Okay. And I don't remember what your book has them attack, but okay, I'm just going to have it attack this resonance form here. And then what we're going to get is we're going to get this intermediate species here. This is my new bond. Goodness. And I have this here. All right. What's going to happen here? What do you think? You think about what I need to do. What do I need to do? I need to kick off the OH group and substitute it with the OR group. Okay, so I got to get rid of my blue OH. How do I get rid of the blue OH? Come on, guys. Are you guys just so brain dead from yesterday? Is that what's going on here? Proton transfer. Or are you guys just taking an excessively long time to type? Yeah, I'm going to do a proton transfer. Perfect. Right? And so now I have this. And by the way, it doesn't matter which OH you transfer it to. It really doesn't. So now I have a good leaving group. I'm going to reform the bond. I'm going to have this intermediate species here, which, by the way, the pK of this guy is -7. Can you believe that shit? And then my water that just left, or the conjugate base of whatever it is I use, can come in and remove it. And voila, I have an ester. Oh, yes, that's true. I keep forgetting about that. Yeah, in the classroom, you guys can just yell shit at me, but here, not so much. Here, not so much. All right. Questions about that? No? It's pretty straightforward stuff. Now, if I were to take this bad boy right here, if I were to take that, I get nothing. But if I were to take this delta hydroxy carboxylic acid, you're like, what? Delta hydroxy carboxylic acid. And react it in the presence of acid. what would I get? An anhydride? You're in the general area, but for an anhydride, I need 2 carbonyls, correct? That's fine. That's fine. At least you're looking. We talked about this at the very beginning of the, well, after the IR section. Does anybody remember? A delta lactone. Okay. And so, yeah, that's right. We're going to have an intramolecular Fischer esterification. Okay. First step, protonation. I'm going to form this intermediate species. It's going to look like this. Okay. Then this, those are lone pairs. Don't look anything like lone pairs. The lone pairs on the oxygen atom, of course, will attack. And this is where stuff starts to get a little wonky. I'm going to have this intermediate species. What's going to happen now? Proton transfer. I'm going to form my good leaving group. It's going to look like this. I draw my hydrogen on top, although I think that looks so ugly, but it really doesn't matter. Form my carbonyl, get my dehydration. Form this intermediate species here. Water will come in, deprotonate, form my final product. Booyah. Booyah. Fun stuff. Fun, 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 fun for everyone. Fun for everyone. Right? Oh. Yeah. This part of the test is not that hard. I don't remember. Yeah, the next chapter is new. The next chapter, we're going to start doing reactions at the alpha carbon. So that's when things are going to change a little bit. This chapter, honestly, I have contemplated putting this chapter with the other exam, but then that's 5 chapters, and that's just way too much. 4 chapters. So, because this could go with a previous exam or, not so much with this exam, but it works. All right. Questions about that? Now, your book says, your book says that this is going to happen here. Okay. So this is going to be greater than like 100 degrees Celsius, which is pretty hot. Your book says that this will happen here. Does anybody have any issues with this? She does stipulate that this is a low yield. But why do you think I'm having such a problem with this reaction? Why do you think I'm having such a problem with this reaction? At the very heart of everything, carboxylic acids are acids by definition. And what category does ammonia or amines fall into? What are they? They're bases, exactly. And when it comes to proton transfers, okay, proton transfers, because all you're moving is a proton, have a very, very, very low energy of activation. Okay, if you have a proton transfer step, protonation, deprotonation, whatever, that's always going to be the lowest energy of activation in your reaction. Okay, and so I've said it before, but I'm going to say it again. Acid-base chemistry always happens first. Why does it always happen first? Because it's got the lowest energy of activation, so it's kinetics. Okay, the kinetics are very fast, and so most likely the outcome of this chemical reaction would be this. Okay, would be this. Now, I have ammonium now, okay, and I have a carboxylate. So now what I have done, what hold on, I'm just going to refresh myself on how to speak English or speak at all. Teaching during mold season. By the way, it's July. Doesn't Mother Nature or whatever you believe or don't believe in, don't they know that everything should be dead and my allergies should be completely gone by this time of the year? What the hell? What the hell? I have like this sweet spot from like July to September where I have zero allergies. I feel like I got to roto-rooter my sinus cavities. I've been using the neti pot. I even broke out the Vicks. Because Vicks fixes everything, right? It is because of all the rain. Our mold is off the charts right now. Anyways, let's go back to this. Maybe I should just fly to Arizona and just let my sinuses clear out. Oh, we have dust too. It's the apocalypse. That's it. It's just the apocalypse. I don't even know why we're bothering with this. Humans are going to be dead soon. Okay, so back to this. Just back to this. So now this is a very poor electrophile. Why? Because now I have all this extra electron density that's going to cover my electrophilic carbon. Okay, so this is a poor carboxylic acid is a poor electrophile. And then this would be a poorer electrophile. So now my carboxylate is just like a crap electrophile. And what about my ammonium? Okay, is this a base anymore? Is ammonium a base? Can it be a nucleophile? Can it be a nucleophile? All bases must have. By definition, what must all bases have? Every single base. Lewis, Arrhenius, Broadstead Lowry, all of these different definitions for bases, they must have a lone pair. That's exactly right, Jason. That is exactly right. And now the lone pair I did have is tied up in what? It's tied up in bonding. There is no lone pair. So now it's non-nucleophilic. And so does this happen? Okay, so this is one of those things that you're just going to have to, and I hate to say this, I really, 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 really hate to say this. You're just going to have to memorize that when you have an amine and a carboxylic acid, and this is key, when they add heat, the heat makes the difference. You're going to get this, okay? Because if you just have no heat, you're going to get this, what I just drew, okay? What I spent all this time talking about. With no heat, you get this, okay? And so, again, this is one of these things that drives organic students crazy because you guys think that it should be one or the other. And in all actuality, you probably get a combination. You have a nucleophile, okay, but you also have a base. So sometimes you could get substitution, okay? And so again, this is why it's key, make sure that you pay attention to the delta symbol, the capital delta symbol, this guy right here, okay? So does that mean that we're kind of screwed? No, we're not screwed at all. As a matter of fact, and I did this reaction, I don't even know how many times as an undergraduate, as a graduate student, I would take carboxylic acid, I would react it with an amine. I'm going to use ethylamine here. But again, as always, NH3, primary or secondary. So of course we have to have that proton at some point. Okay, in this reaction, we're going to have to deprotonate that nitrogen. So almost every reaction I show you guys with an amine, it can never be a tertiary amine, right? Because tertiary amines can't be deprotonated. Okay, and we're going to use a catalyst called DCC, and we're going to get substitution. Hold on. And we're going to get substitute, wrong color. Okay, and the DCC will give us urea as a byproduct, which is the driving force of the reaction. All right, so what is DCC? DCC is dicyclohexyl carboamide. Diamide, I'm sorry, diamide. So what does this mean? Well, it's a diamide, right? So there's the diamide portion, okay? And then dicyclohexyl. Okay. This is DCC right here. And the urea we form comes from DCC. It's how we get the carbonyl oxygen, I'm sorry, the oxygen from the carboxylic acid off, and it's also what deprotonates. I did it again. Takes off one of these hold on, son of a sorry, I didn't just make that sound, but I really did. Mother of God. Pink, we'll use pink. So, okay, so I get that. And then, so let's do the rest. I want you guys to see where everything comes from, because it really does help out with the mechanism later on, even though I know you guys will never write a mechanism because, you know, you're not taking this in person. But I don't know. All right, so I'm just going to make these cyclohexyl groups R's. Wasn't she supposed to do that yesterday? There. And this is urea. So urea is another functional group. And when you see urea, basically this is a urea. Okay, you have a diamide. A diamides are urea. Okay. Okay, so you ready for the mechanism? You guys ready? You're like, I don't know. You are. You're going to be fine. You're going to be fine. So first step of this, deprotonation. So these are basic. Okay. My DCC is basic. Okay. And so I'm going to take my carboxylic acid. Okay. And then my DCC is going to come in, which I'm just going to draw like this. I hope you guys don't mind. It just, drawing all those cyclohexanes just drive me nuts. Okay. And one of these nitrogen atoms is going to act as a Lewis base. Okay. Now, this is kind of a turnaround, and it's something that we've not seen yet, and we're going to see it later on. Okay. This protonated diamide can now serve as an electrophile. Oops. Pardon my bond angles. I'm running out of room here. So now we have this. This nitrogen right here, I'm sorry, this carbon right here is electrophilic, very electrophilic. Okay, very electrophilic. Okay, and so when we have carbonyl groups, we protonate them, right? We make this carbon more electrophilic. Okay, we can do the exact same thing to an imine. That makes this carbon more electrophilic. And so this is kind of a different way of looking at this. Typically, all the carboxylic acid derivatives we've been talking about, they are the electrophile. Okay, but what I'm doing is I'm first converting this into a nucleophile. And then my DCC will become my electrophile. Okay, my DCC will become my electrophile. And so this one is not intuitive. Okay, this is not something that I would expect you guys to get off the top of your head. And so nucleophilic attack. Okay. Sheesh, nitrogen. Nucleophilic attack. Okay, and I'm going to form this intermediate species. So new bond here. Come on. I think my, just FYI, I think my, I wouldn't be surprised if this doesn't crash pretty soon. So I have this proton that I just got from the carboxylic acid is here. Okay, so now I'm there. Okay, now I'm there. So that is the first step of my DCC. This entire chunky will form a good leaving group. Okay, that entire chunky. Now, this is where the amine comes in. Remember, the DCC is not our product, it's not a reagent, it's a catalyst. So now that we've converted our carboxylic acid into something that we can work with, now my amine can come in and it is the nucleophile of this brand new intermediate moiety species thing, chunky, whatever you want to call it. It's going to come in, it's going to do nucleophilic attack. I'm going to get this intermediate species. Isn't this fun? I mean, this is like so much fun. You're like, Doherty, I don't know what you consider fun, but let me see, which color did I use? Which color did I use? Pink. So let's put the pink hydrogen over here. I'm just going to leave that hydrogen as being green. All right, so now I have this, okay? And then I have my DCC chunky attached. Hey, that worked out pretty good. Now, what do you think is going to happen? Actually, the next step of this is not so obvious. So now we have our good leaving group. You're like, oh my God, pay attention to my arrows. This oxygen is going to become part of the carbonyl oxygen at this point. Okay. Did I forget the proton transfer? Oh, I did. Sorry about that. I always get screwed up here. You're like, great, you get screwed up. Sorry, proton transfer, my bad, my bad. That's coming from the nitrogen atom. Hold on, let me just redraw this arrow, it's ugly. There we go, proton transfer. See, sometimes, believe it or not, guys, I don't have all these reactions memorized. Sometimes I have to look and see what I'm doing, and then I realize, nah, that doesn't make sense. That's probably wrong. So now I have this. Now I have my good leaving group. And this is where it's going to come off as the urea. So I have this formation of this bond, urea, break this bond right here. And so now I have my brand spanking new amide plus my urea. And again, you can kind of go back and look at these. I don't want to draw these all in different colors because frankly, I don't know about you guys, but I'm ready to call it a day. So remember, these R groups are cyclohexane rings. Wow. Wow. Wasn't that fun? There you go. I lost somebody. You guys good now? You a little shell shocked? See, it started off as an easy lecture, didn't it? The other good thing about this DCC is your byproduct, urea. This guy right here is soluble in the aqueous phase. So it's really easy to get rid of at the end. Not that any of you guys give a rat's behind about that. Okay. So steps are protonation of DCC, nucleophilic attack of protonated DCC. So let's go through it right here. So, and then so. We're going to protonate DCC, nucleophilic attack of DCC, and I'm going to write it like this, protonated DCC. Okay. Then what happens next is now my amine attacks. Okay. Then proton transfer. Okay. And the final step is carbonyl bond reforms and urea leaves. There. How's that? So it's a 5-stepper. So 1, 2, 3, 4. It's a 5-step reaction. Yeah, it's easy. No, there's a lot of steps. No, that summary was probably good for everybody. Okay, and so let's look at the energy diagram for this guy. Just kidding. Yeah, we will not be looking at the energy diagram of this guy. But again, it is important that you understand that the formation of the urea is the driving force of this reaction. Okay, urea drives this reaction towards completion. Okay, guys, I think you guys are done. I know that I'm done. So if you guys don't have any more questions for me, congratulations on your performance on the exam. And then I will see you guys tomorrow. We will finish up this chapter and start the next one. Fun stuff. All right, guys. Talk to you later. Bye-bye.